Okay, so assume that that's a track. Okay, that's your car. That's the red one is a stoplight. And the right side is another stoplight. And the goal is to go from one stoplight to another stoplight as fast as possible. Okay, so let's say this is x equals 0. Clearly, this is x equals d. Well, let's just make it like this. X of t equals 0 equals 0. And then x at t equals t equals t. Okay, so d is the distance between the stoplights. And then our model for the car is very simple. It's basically the acceleration, or x double dot, equals the either the u could be positive, in which case it's the accelerator pedal. If it is negative, it's a brake. And you can, let's say, in some units, u can be between -5 and +5. So you can accelerate up to 5 units and or decelerate to -5 units. Okay, and your goal is to minimize the time. Okay, and I forgot to say here that since it's a stop sign, you better stop. So the velocity should be 0. So do you know what the solution to that problem is? I can't hear it. Just go 5 and then for a certain distance and then do -5 and stop, right? Okay, so that's the solution. Let's see if we can get this same solution when we do this using whatever we learned so far. So first I need to, before I solve this problem, I need to formulate the problem. And I would say that when you see a problem like this, don't just start coding this. You need to write the problem in terms of the same language I described earlier, which is at a cost, at constraints, at bounds. So unless you have that, it just becomes hard to write this down and you'll probably make mistakes. So what does the formulation look like? Well, so formulation, we have to minimize the time. So I need to integrate the time. Now that is clearly simply t, right? It's not, I don't really need to put the integral there. I just wrote it down, doesn't really matter. Now minimize this integral. And the question is, what are my optimization variables? U is clearly an optimization variable. Now I could keep time not an optimization variable, but it turns out that unless you put it in here, it's very difficult to really solve this problem. So t also happens to be one of my optimization variables. Okay. You can think about, try to do it without t, you'll see it's really hard to do it. So I'll just put that in optimization variable. It's always okay to put more variables, and some of them may turn out to be very trivial, in which case the optimization will just discover it. So for example, I could put the initial position velocity as optimization variables, right? But when you formulate it, it'll be obvious that the initial position is 0 and velocity is 0. So you could either put it there and then write it as a constraint or just eliminate that. It's up to you. The next is our dynamics. X1 is X2. Let me tell you what X1, X2 is. X1 is the position. X2 is the velocity. So the first one is saying that the rate of change of position is the velocity, X2. And the second one is saying the rate of change of velocity is the control, which is U. So that's my system dynamics. I have bounds on my controls. And then I finally have these constraints on the motion, which is the position at time t equals 0 is 0. Position at time t equals capital T is d, and I'm just going to assume some number, fine. Okay. And then x2, which is my velocity at time t equals 0 is 0, and velocity at time t equals capital T is 0. Okay, so we can see that the first one is the cost. This is these are sort of constraints. Okay, these are constraints too. And this is my bounds. So the constraints, the first constraint is how the system behaves, and you're not allowed to violate them at all, right? If you violate them, that means your system no longer behaves like a car. The last one are probably less critical. Like it's okay if you don't reach the stop sign with a perfectly zero speed. It's okay if you are a little slow or fast, right? But the first ones you cannot violate. Now you could put them like that in the optimization. That's absolutely fine. Or we'll just ensure that they are met in the way we formulate it. And then the bounds are probably hard ones because you don't really have ability to go beyond 5 and -5. Okay, so that's the formulation. Now I'm going to show you two methods to solve this. And the reason why it's called constraint optimization, well, trajectory optimization, is because what you're solving for is not the value of x1 at an instant of time. Like, for example, that f of x, which I showed you for the first two problems, that was a cost and you solved a static problem. In this case, you're solving a dynamic problem. You're computing how x1 evolves as a function of time and x2 evolves as a function of time. x1 is a function of t, and x2 is a function of t, is basically defining your trajectory. And that's why it's a trajectory optimization problem. So x1t, x2t are the unknowns, and this is basically defining the trajectory. And that's why it's called trajectory optimization. Okay, so now we know that. Now let's think a little bit about what exactly we are told to do. We are tasked to compute t and u. Okay? T and u. Now the t is nice because it's just a one-dimensional, it's a scalar. So you can take a value from 0 to whatever you want to bound it to. The issue with u is that u is a function of time. And the question is, how would you define u? Well, u is some profile. Okay, so u of t is actually infinite dimensional. Because there's a value for u of t at, let's say, at 0, there's a value of u at 1. Between 0 and 1, there are infinitely many numbers from 0 to 1. So technically speaking, you need to evaluate u of t at every single point from 0 to whatever capital T is, and there are infinitely many numbers from that. So instead of solving that problem in infinite dimensional space, we use finite dimensions to solve it. And that's because the optimization method I showed you is all relies on finite numbers, right? X1, X2, those were finite numbers. So we need to convert this problem from infinite dimensional, convert problem from infinite to finite dimension. Okay, so the way we do this is as follows. Here U of t is what is infinite? This is U, this is time. So we'll assume some grid. And in this case, we'll assume a uniform grid, but you can have a non-uniform grid too. It's just easier to have a uniform grid. Okay, so at each of these points, I have a value. So let's say U of 0, U of 1, so on till U of n. And then I'm just going to stick to drawing just a line between them. Now you could have a different way of doing it. You could have maybe a line has a equation is linear in time in this case. But if you had like a curve, let's say a third order curve, a cubic spline will be much more smoother. That's fine too. Just that linear is easier to code and to think about. So I'm just using a linear function between any two grid points. Okay, so these are grid points. Uniform grid. And these are the values. And then you can see that as the n goes to infinity, you will recover the true solution, right? Because then it becomes an approximation to that curve, which I showed over here. But clearly, you don't solve it for infinite points because then you just can't handle it. So what typically people do is they'll solve this problem for some, say, 10 points. And then they solve it for 11 and 12. And then see if that cost goes down as you increase n. If it goes down, then you have to keep increasing. But if the cost doesn't change much, then you probably are very close to the optimal solution. You don't have to bother increasing n's. But the smaller the n, the better it is because the problem is smaller. Now, I'm going to show you two methods to solve this. One is what is known as the collocation method. The second approach is called shooting method. Okay, and if you read papers on optimization, you'll say in passing, this was solved using collocation method. So this is going to basically get into the details of how these methods are used. Okay, so I'm going to formulate the collocation method first, and then probably next class we'll see the shooting method. Okay. The key thing about collocation method is the word collocation means you sort of assign values at specific locations. So what we do is we try to satisfy the system dynamics at grid points. Okay, what I mean by that is we have this equation x1 dot equals x2 and x2 dot equals u. We'll try to sort of discretize these equations and then try to satisfy those equations at grid points. Okay, and that is the main way in which we would distinguish collocation with shooting. In shooting, we'll basically integrate the equations. We'll satisfy that equations more exactly than we do with collocation method. Okay, so I said the key ingredients to solving any optimization problem is the cost, the optimization variables, should put that here. So we need to specify these things: cost, optimization variable, and constraints and bounds. So if you have these four things, we can then put it in that software Skippy, optimize, and solve it. So let's define them one by one. So the first is optimization variables. T is the time, that's a scalar. And then we'll specify u, I, where I goes from 0, 1, all the way to n minus 1, where clearly u, we have u0, u1, so on till un minus 1. So that's the time axis. This is, okay. I should just put I equals the values are actually here. U0, U1, and so on. And then we'll place them at equal points, right? T equals 0, dt, 2 dt, so on till capital T. B, we want the objective. Okay, we don't have to do much work here. We just know that the objective is time, and it's okay if the objective is the same as the one of the variables. Absolutely fine. Okay, next we put constraints. Let me move to a new page. Okay, so first one is u of I is between -5 and 5, right? And that will be, of course, at each point. So I have a grid of n grid points, so it'll be at each grid point. X1 at I equals 0, or just put 0. Should be 0. This is saying that starts at position 0, ends at position 5, starts with 0 speed, ends with 0 speed. Okay, now we've specified all the constraints with bounds and the constraints in state. Let's get the equations. We have x1 dot equals x2. So what we do is you write this as x1 t plus delta t minus x of t divided by delta t is x2 . Now I wrote this down for the first time step, but you can write this for every time step, right? So which will, it will become x1 I plus 1 equals x2 of I plus delta t x2 of I. So you see that I used forward difference or Euler's method to discretize the system dynamics. So remember that I'm going to ensure that this equation is true at every grid point, which means that there's no guarantee that it is true between the grid points. And that's one of the limitations of collocation method. It only ensures that it's true for the grid points. So I can write a similar expression for x2. x2 I plus 1 equals x, this should be x1. x2 I plus delta t u of I. Okay, so now let's do some counting. Let's count the the number of different things, right? So let's count everything here. We have yeah, I think okay, let me just do it this way. So this is n number of equations or constraints, because you have to grid point. There are 4 here. This is going to be n, and this is going to be n, right? You try to satisfy that n points. So there are n plus n plus n, that's 3n plus 4 equations. Okay. Let's go here, and then the objective is 1, which is what it will be. We have 1 for t, we have n for u of I, and it turns out that I forgot to put this, but in this collocation method specifically, since we're trying to ensure that those values are true at the grid points, the x is also a part of the optimization. So I need to add those, which is something I forgot to add. So I would have x1i and x2i will also be unknowns. So there'll be n here, n here. So we have 3n plus 1. Okay, we have 1 more minute. Let me show you the code which will do this. So I have collocation. Okay, I'm going to run this, Control Shift P, and it basically gives me a plot of x, x dot, and u, and you can see the control. Just make it pause for a little while longer. Okay, so that's the position, velocity, and then the acceleration. So it goes 5, and then it goes -5. The reason why it goes -5 is because of discretization. If I increase the number of n, then it probably give me the right, which is basically going +5 and then -5. I've used, in this case, SLSQP. Okay, so give me a minute. It's already 3:50, but I'll just finish this. So the cost is the first variable, which is time. The nonlinear function are basically I initialize the position, velocity, and u. I try to satisfy that relation here. So position I plus 1 equals position I plus velocity I dt. In this case, I actually did not use the forward difference. I used midpoint rule. So instead of taking ui plus 1, I took the average of the last two. It's just one way of doing it. You could also put 1 times ui plus 1, which I have in the notes. And then I have the equality constraints, 4 for the initial and final position velocity. Then I have these constraints for, well, these are the two constraints for the difference, the system dynamics. Since x is so I have also x1 and x2 as optimization variables. I need to put bounds. So I just randomly put the bounds for the x to be 0 and so every instant of time you have 0 and d. I know that x cannot be greater than 0 and d. So I just put that, which is really a big range for the bounds. I put a velocity minimum maximum of -10, +10 was not specified, but I need to put some variables, and then I put the constraints for u. I started with 2, and then I gave all zeros for the other ones, and then ran it past the optimizer, and then it gives me that solution. So next time I'll show you how to do it with the shooting method, and we'll get the same answer hopefully. Yeah, see you on